next time. And you know what I realized? Well, I could just write out the function for the electric field, right? So I'm back in Maxwell's equations land. Maxwell's equations talk about electric field. So instead of E, which is also energy, and that sucks, I'll just call it an electric field. Has some magnitude. Oh, and I noticed when I was looking at the video, I was like, I cannot see that pi, so I will write bigger. I always need I need a few days to get back in the groove. Okay. So that's the electric field, and it's a solution, so because of Maxwell's equations tell us this. This is obviously one-dimensional. Again, I'm writing elec so that when we have E for energy, it's not the same letter. I've been doing this so long, when I see talks and maybe they have the same letter for two different things, it just rolls off me. And not because it's like, oh, I instantly know what it is. Maybe I do. It's just I don't worry about such details. I know that you do, though, because you're seeing this for the first time. That's why I'm going to try to be very careful. Okay, anyway. So Maxwell's equations give us this. This is a solution. And as always happens, somehow nature reveals itself only in the form of a differential equation, which sucks because it's a nightmare to solve. Well, once you do so, you can plug this thing back in, and then you get something out of it. And last time what you saw was we came up with the formula for the speed of light. Not that we can't guess what that is, but there you go. Okay, then we started thinking about how to, I'm going to change the notation here. I'm going to call this a wave equation. And we're not going to worry about the amplitude, the normalization, because that's a bit of a thing when it comes to wave. Understanding normalizations for waves is unpleasant and weird. Okay, here's energy, right? So we multiplied and divided by h bar, but we realized that we had momentum. And then this ends up being h times the frequency, which is the energy of the wave. And then you plug that sucker back in, and therefore you plug that back into the wave equation, the differential equation, and you end up with some innards that have to be zero. This has to be zero, the interior, because this part, the constant's not zero. That doesn't make sense. I'm just writing the wave equation again. The wave equation isn't zero. It can be zero, but maybe just temporarily. So therefore, all this is zero. So that's zero. And what you get out of that is E squared is P squared C squared, which again is, that's the theory of relativity for a massless particle. And what you get out of this, now last time I learned what the speed of light is, what you get out of this is that you can show that light has momentum. So anyway, we made this really trivial change. Like we didn't really do anything. All I did was I multiplied and divided by h bar in the wave equation, and all of a sudden I learned something new. Go figure, right? I still kind of make my head spin a little bit about why that worked out that way. I don't know why you can multiply and divide by a constant and then learn something new. Just seems weird. Anyway, but it does work. Okay, then what we did is, okay, so what if you do this? Again, energy squared. Let's throw back in mass. So this is the real equation for energy. So what you're going to do is you throw this into the interior and you reverse engineer. You reverse engineer a wave equation that would provide you that information. And I still need to post the paper. I stole this from a paper, by the way. And I'll put, instead of setting it equal to zero, I'm going to write it out in a more Schrdinger equation-like way. Okay. Okay, and so there you go. And again, this is the Klein-Gordon. I think I'm misspelling that. such a, as I got older, I don't spell so well. Gordon. Yeah, it's a different, yeah, Gordon. Okay, so it's thought Schrodinger got here, and then he realized what he did was he solved the hydrogen atom using this, and it doesn't work. And he was like, uh-oh. Then what he does is it makes some simplifications and derives the Schrodinger equation. And if you actually look at his original papers, they're incomprehensible because they're in German. But what they are is they're actually a solution to hydrogen. And everyone knew that if you get hydrogen right, you had to be right. Later, Klein and Gordon would come across, they're like, okay, that's fine, but there's no speed of light in the Schrodinger equation. There should be, because relativity is a thing. And as I showed you, they're not inconsistent. So they derived this, and they were like, cool. If it just doesn't work for electrons. It works for a lot of other things, but not electrons. And so that's weird. It would have been awesome had it really worked, because then you would have had all the benefits of quantum mechanics, but it would have captured relativistic effects too, which the Schrodinger equation doesn't. And that includes things like, spin up and spin down are allowed, to spin up are not allowed. It also captures, what the Schrodinger equation does not capture is spin-orbit coupling. We're going to go over that, but in case you don't remember, spin-orbit coupling is what allows, say like an excited singlet state to turn into an excited triplet state, which is where that's the difference between something that fluoresces versus something that phosphoresces. Fluorescence is like dyes, like fluorescein. Phosphorescence are things like, all the things that are phosphorus, including lanthanides. I'm thinking Larry Miller. Larry Miller is a phosphor guy, works with lanthanides that are very phosphorescent. So he's one of the most well-known people in that field. He and I work together a lot. So anyway, it would be cool to have the Schrodinger equation plus relativity, but we don't. And this doesn't work. And so what happened was Dirac, and I'm going to show you the Dirac equation. Dirac resolves this by doing this. So imagine putting this into the wave equation. He takes a square root, and I don't know why this would work. It does. I don't know why this would work. And again, I have to write bigger. So he just takes the square root of the thing. So he basically, he solves for energy, and he makes it work with relativity by simply taking the square root of Einstein's equation, and then he gets the Dirac equation. I should be teaching you the Dirac equation. It's the wave equation. It gets Schrodinger's equation right, but it also gets relativistic effects right. It predicts spin. Schrodinger doesn't have spin. Spin up, spin down doesn't even exist. You have to force it to exist within the Schrodinger equation. Dirac naturally spits out hey, you're just trying to describe an electron, just so you know, you have to have spin. Dirac just does it on its own without you forcing it. That's considered a good thing. It certainly sounds good. The problem is that this is a freaking nightmare to deal with. And so the question is, should I teach the Schrodinger equation or the Dirac equation? Well, bang for buck, right? It turns out that relativistic effects in chemistry, they're just not, it's not that important to get the basics down. The Dirac equation, it's really hard to get an intuitive sense about how this works. You just get lost in the mathematics and everything just becomes a math exercise. Whereas the Schrodinger equation, you can get an intuition about how things really work. It's just easier. And as I said last time, I don't really want you to come away from here trying to memorize some specific examples versus altering your way of thinking. Okay, so what Schrodinger did was, so he, instead of this, which is true, he makes an approximation. Oh, sorry, equal. This is equal. He factors out MC squared. And, sorry, I need to write bigger. I was going to need to write bigger. P squared over M squared. Okay, here's an approximation. MC, sorry, my handwriting will get bigger, better, I promise. Okay, 1 plus 1/2, so it's like a Taylor series. So that's basically, he's taking this and making a Taylor series out of it. Again, P is momentum, M squared, C squared. And then this ends up being MC squared plus P squared over 2M. So you recall that the Schrdinger equation has P squared over 2M as the kinetic energy operator, so now you're seeing where that comes from. Okay, and again, I'll post this paper. When you do this and you put that in here and you go from there, you're 4 steps away. I don't want to do it. I found it just like, oh, what? I mean, I can follow 4 steps. I'm sure I could write it out and really like get it, but it's kind of a pain. And so I'll post the paper, but let's just say that if you're going to work with E instead of E squared and you fit that into here, then you get the Schrdinger equation. And I'll add potential. So here's momentum squared over 2M. Okay, so all this derivation does, it just gives kinetic energy, but you know if you have potential energy, then you need to throw that in, and then that's equal to the energy. E is now energy. So there you go. That's where it comes from. And again, this is still a pain in the ass to deal with, really. But nothing compared to the Dirac equation. But I do want you to know that the Dirac equation is the right one. This is an approximation. And the nature of, so I still see the speed of light in here, and so that means that this guy is still relativistic, but those other approximations, you don't see C in here, so it's not relativistic. And what you lose as a result is something we can kind of fix up after the fact. That's the idea. Okay, so any questions? Like I say, I'm not going to even bring this up again. I just think it's a little bit of a cool history lesson. I also want you to get used to seeing differential equations that go on and on and on. I want you to remember that e to the ix is cosine plus I sine. Imaginary numbers are important. Imaginary mathematics is important. So I hope you're up on that. If not, come by office hours. Okay, so now motivation for quantum mechanics. Again, today will be an easy day. I'm going to draw some pictures. I'm going to show you something real cool. Back in the 20s and 30s, people started trying to defeat quantum mechanics, Einstein especially. Einstein didn't believe in quantum mechanics. So what I've got is a little chamber here, and the chamber will have silver atoms, and like a bar of silver, and there's a flame. A burner would look like this, so it's like an acetylene torch. Okay, so you got this thing, you got silver in it, and silver atoms come flying out. And these are, so I went to grad school in California, and there was a lot of, these are like molecular beams is what you call these. Heat up something, get it like a bunch of bees in a hive, and put a little hole in it, and only if you have the right trajectory do you get out of the hole. And that means you're almost going straight. And they have these weird ways, you can actually cool this down. You can actually add like argon atoms in here, and what they do is they'll like touch the silver and bounce off, and they'll actually cool it. So you can make these atoms in the gas phase going in a direction, and you can make them like really cold. You can get them down to like 1 Kelvin, doing all these tricks. Robert Gordon was the last faculty here. People just don't do that kind of work so much anymore because unfortunately it's really expensive. Robert Gordon was one of our last faculty who did these type of molecular beam research. But anyway, the history of physical chemistry, modern physical chemistry, is that this was a big deal. And a lot of people, if you were in P-Chem, this is what you would have been doing, these types of molecular beams. Largely not done anymore. A bit of a shame. It's just too expensive, really. It's the way of the world. Let's see. Well, I'm going to tell you another thing. Whatever. So silver, by the way, I thought I wrote this down. Silver, did I not write this down? Silver atoms are, did I not write this down? What the heck is wrong with me? Silver is naturally, has a 5-1s electron configuration. So the lower orbitals are all filled, and there's only one electron in an s state. That's kind of important to have a single electron and it be in an s state. Those are details that we don't need to worry about. This is, by the way, this is also the very first part of the book. And as if any of you, some of you already told me you've been looking at the book, it's really confusing, unfortunately. It's just written in a very confusing manner. So, like, the book will go into great lengths of detail about why you need to have silver do this, whereas I'm just telling you it is important, but we'll go into more detail later why that is. So anyway, so we have a 2-slit experiment. The slits are separated by length A, and because the silver atoms are mostly on the linear trajectory, we're going to call this dimension X. I know we want to call it Z, right? But let's call it X. And here's minus A over 2, and here's plus A over 2. Okay, and then what you're going to do is, so let me turn this 90 degrees. That's 9 degrees, what's wrong with me? 90 degrees. So P of X is the probability that you're going to observe at silver atoms plate the detector. And the way these work, by the way, the detectors work, you can literally have materials that are phosphorescent. Zinc selenide would work. If something hits it, pings it, I think it's called like triboluminescence, it'll just glow if something hits it hard enough. And then behind it is a regular CCD camera. The technology is actually, you can imagine you can actually just plate the silver and measure it. You can just literally see it. Or you do something a little bit more sophisticated, like I just described, and you can digitize the absorption, the striking of the silver atoms. And the technology is not really as hard as you think. So what we're going to do is close slit number 2. Let's say that one's number 2. And what you would see is a probability distribution of the atoms hitting that spot like this. You can imagine where I'm going with this. 0, A over 2. Close number 1. And what you see is the atoms build up over the other slide. I mean, again, this is like middle school students would understand this. Right? And, their intuition, middle school students would probably just figure out what you would expect with both of them. Both of them was CM at 0. What happened when both slits are open with matter coming through is, of course, unbelievably annoying. You get an interference pattern. You get an interference pattern from atoms. What? Light does this. When you were a little kid, you probably saw that Isaac Newton picture of him holding a prism, or maybe you played around with this a little bit. Maybe in school you had an actual diffraction grating. Sure, light does this, but this is matter. So this is like mind-blowing. It's called the Schrdinger Experiment, I don't think I have this written, 1924 or something. Anyway, so this is what they found. Again, you would expect like just 2 Gaussians, but instead you get an interference pattern. And one of the things that people thought, because look, they were like, what the heck is going on, right? You gotta go back in time to when, remember like 1920, the whole concept of atoms is actually kind of new, right? That's something that is within a living person's memory. So you may think that they're bouncing off each other, the atoms coming through the slits, like versus 1 versus 2, like they hit each other. So what you do is you reduce the intensity like a lot, and you can do that by just like not turning down the burner or something. So that you know for certain only single atoms are coming through the oven, and it still happens. So they're not hitting each other and having some weird mechanical interaction that's causing this, causing something that looks just like a light diffraction pattern, but probably is something else. That's not happening. And number 2, they're doing it on their own. So that's disturbing. Okay. Now what we do is, let's say that we're going to have an equation that describes these atoms moving as waves. So again, I'm mostly doing this because I want you to get used to EPR, because that's what everything turns into eventually in quantum. Everything is EPIK something. Remember, K is 2 pi. I'll write it down. K is 2 pi over lambda. R1, R2, and I don't want to leave you hanging. You know, when I see K, I often start thinking, oh, that's something so complex and complicated. It's just 2 pi over lambda. Question?
So you're trying to explain the Schrdinger experiment to show the particle nature, right?
You lost me. What was that?
You're explaining the Schrdinger experiment to show the particle nature, right?
Yeah. No, actually, what I'm going to try to do, I mean, I've shown the that is behaving like a wave, right? So what I'm actually about to do is I'm going to show you how an attempt to defeat it.
If you don't explain the introduce the spin factor, then the Schrdinger experiment will not stack, right?
Again, I'm sorry.
If we don't introduce the spin factor, minus half plus half, then now the figure looks like a double slit experiment, right? Just like a light. Now here this seems like a wave nature.
Yeah, right. So
but we need a particle nature. So we need to introduce the spin character, right?
No, hold on one second. Okay, so the particle nature does this.
Yeah.
Right, and so the particle, if these were particles, then you would have expected, I didn't write it, I didn't draw it just because I thought it was, just unbelievably obvious. You would expect that for particles. So there's no need to discuss the particle nature further because it's just wrong. And the way I would do that is I would just start writing mass is equal to, mass times velocity is momentum, and calculating trajectories based on Newton's equations, and I would get just the 2 Gaussians. Okay, that's for one, in physics 1 you learn to do that, so I don't think there's a need. Number 2, you would get the wrong answer. So now I'm using waves because, for one, again, as particles, forget it. We already know it's wrong, so I'm going to use wave equations. Now, in terms of does it need to be spin half? Actually, this isn't the Schrdinger watch. Schrdinger watch uses
Schrdinger was the spin half and put the magnets.
Put magnets, right?
So this is like the dual length double slit experiment.
Yeah, this is the double slit. Sorry, no wonder I didn't have the. Some of the notes I'm thinking have come later when I talk about Schrdinger watch. Sorry about that. Yeah, you know what? It doesn't have to be spin. So your question was about spin. It doesn't have to be spin half. Yeah, I'm kind of mixing them up too. It is silver. They did do this with silver, by the way. But it doesn't have to be spin half for this to work. It does for Schrdinger watch. You can actually, if I recall, I think you actually do this with like C60, which is diamagnetic, right? Which means non-magnetic. Yeah. So you can do this with anything. Yeah. Okay? Yeah. So yeah, so please isn't too hard. Now, another concept to get used to is that you're observable. So when it comes to light intensity, I was talking about electric fields, but you actually don't observe an electric field of light. You observe the intensity of light. And just by the very definition of the word intensity, you should automatically agree with me. The intensity of light is the electric field squared. And if we have complex notation, then we need to be doing this. And again, I'm hoping that your knowledge of complex mathematics is that you recall that. It's in that silly textbook I sent you, complex conjugate times the thing. So anyway, I hope you're up on that. If not, just let me know. We'll sit down together. And again, it's in my silly little textbook. And again, I'm assuming, notice that I'm assuming it's a wave. So to some degree, my results are fixed because I've already made them a wave. So I have to give them an appearance pattern. Okay, so what I'm trying to do though, for one, I want you to get used to how complex mathematics works. Also remember that absolute values are observable, so that's important. Sometimes you can derive crazy things with quantum and say, no, wait a minute, that could never be right. And the answer is you've figured out a wave function, but the observable is the wave function squared, the absolute value of the wave function. And sometimes you write a wave function that does something really bizarre, like, oh, I can't believe how strange that wave function is. And the strangeness that may be just like mind-blowing and completely unphysical will go away once you square it. And that's the only thing you're going to see. So heads up on that. Okay, so again, complex mathematics does this. The part that you expect. So this part, absolute value of 1 plus the absolute value of 2, this is the particle nature. And then you end up with, in here, I'm sorry, I've run out of room, 2 times the real. I don't quite remember how you solve this. This is a standard for any 2 complex functions. This is how it works. And I always have to, whenever I look at this, I'm like, wait a minute, is that how it works? I have to write the whole, I give myself a function, I just make one up, and I write it all out. And it takes a little while. It's actually kind of a pain, but I do find that this is the case. So you see something that is kind of sensible to our middle schooler, and a part of us that this is what this whole class is about, is what the hell is this other term, and there's your wiggles. And so, yeah, okay, now, I told you we were going to do something kind of interesting. So again, just to get used to this complex math, get used to this formula, you're going to be doing this over and over and over again. And it does turn into this. You're going to see this a couple of times. We don't use this all the time, but you're going to see it a few times. Okay, now as I promised, the cool thing about this is that people started trying to invent. So like if you're Einstein, you just think of ways like, oh, if you could ever do this experiment, quantum mechanics would fail. He literally did that with, it's called the EPR experiment. The Einstein, Podolsky, Rosen, these 2 birds, they all, three people, they thought of a way to defeat quantum mechanics, which was not done in their time because they didn't have atom smashers, but in the 1960s, 70s, 80s, in the 1980s, the EPR experiment was actually performed. It's when you take an atom and you bash it apart, and you send 2 electrons down in two different tracks, and you bend one with a magnet, the other one responds, even though they've gone a mile apart. And Einstein said that would never happen, and it did, so he was wrong. So anyway, so here's an attempt to beat this. Okay, and to understand that, I have to, I'll tell you what, I can go back here to save myself a little bit of effort. Okay, so people want to figure out what the heck is going on, so they're going to try to beat this. So let's make a vector R1, and let's make it visible on a video. Let's make vector R2, and R1 minus R2, so the distance between them and I think this is exact. So this is distance L. So we're going to have L squared. So, you know, what's this distance and that distance? Square root of the square. L squared plus the vertical displacement, which unfortunately I've called x. X plus a over 2. All right, now what I'm doing is, instead of L squared plus a over 2 squared, what I'm doing is I'm calculating the difference of these vectors for any position along x. And again, that looks awful. I'm still getting used to. Okay, so length squared, height squared, square root. Okay, then you do the same for the other one. It still travels the same length, but the x position is lower. Maybe I've gotten these reversed, but anyway. Okay, so there you go. And again, don't mind my foot keys. God, this thing is freaking heavy. Jeez. Anyway, okay, so now what you can do is you can approximate this as ax over L. I'm not sure how. I don't care that much. Okay, so you know what? I needed to mention something here. God, I'm sorry. When I'm looking back at this, I knew I had done something wrong. If you say that epsilon squared is the intensity, what you get is there's a constant plus, when you have the real part of two complex functions, it ends up being a cosine. So, sorry, I forgot to write this down. Maybe I should be more familiar with my notes before class. Anyway, okay. So again, we're going to try to design a way to defeat this system. Or maybe probe it, understand it. Why the heck do these atoms know how to avoid each other? How are they doing this, right? This is so strange. I'm going to start trying to probe this thing, and so I know that this is true. I mean, I can derive it and I can measure it, and so I need to know what R1 minus R2 is, and now I've done that. Okay. Okay, so therefore, the intensity is modulated by like cosine. Okay, K is of course 2 pi over L, 2 pi over lambda, AX over the length. Okay. Okay, so you know, it's periodic. Let's see here, from the periodicity. You always figure out where you go from 0 to 2 pi, and that's the periodicity. So therefore, the periodicity is L lambda over the slit distance. So anyway, okay. Now here's the trick. So I told you we're going to try to beat this. We're going to try to understand it. And here's what you do. Keep writing over this thing. I try not to do that, but I can't help myself today. Okay. What you do? Okay. Any of you, are you working with lasers? Okay. Cool, right? I did laser. I was a laser guy. When the laser's on, you can see the beam, right? You shouldn't be able to. If you had a dust-free room, would you still be able to see the laser?
There can be interference patterns.
Well, then, for the most part, like the laser traversing space, you actually should not be able to see it unless there's dust. Yeah, you shouldn't have dust.
Yeah, scattering.
Yeah. Now, actually, if the laser is very intense, then it can start scattering off air molecules. And in fact, in physics department, they have lasers so intense that they actually have to put them. They have to traverse the board, their experiment in vacuum.
Yeah, they have.
Oh, anyway, so here's the point. So a laser can bounce off atoms and scatter, and that's why clouds are white. So here's the idea. You're going to have a laser, and you're going to have an eye. This is kind of creepy, but this is how we do this. You have an eye to look at these atoms coming through these slits. And again, you're just trying to interrogate it. You're trying to see which one goes where. And maybe then you can figure out, maybe then if you knew which way they were going, maybe Isaac Newton's theories work just fine. I don't know. This is the idea. Shine light on it, and when one of them pops out of one slit or the other, you'll know it. And then your detectors, we have detectors that can see single photons. So an atom striking a surface, I can probe that, so I can know where it goes and which slit it came out of. So now I know everything. And then I can start figuring out what the heck is going on with this stuff and why this whole wave stuff is wrong. Okay, now when you do that, we go from, I may not be drawing it right, okay, that bothers me. The world will explode if I don't get it right. You go from that to on. You're going to love this. Swear to God they tried this. You turn the light on and the damn things stop doing it. Swear to God that happens. Right? So you can't even start trying to tear this down, trying to show why quantum doesn't work. You're going to do that by at least figuring out what the heck is happening. Then you'll do something more clever later on. But then the whole thing that you're trying to interrogate, the whole effect disappears. Screws you, right? So now you can't say that you can undo the underpinnings of quantum when you're not seeing quantum effects to begin with. Okay, now why is that? Here, I'll work it this way. Why is that? Now this is kind of cool. Okay, so what you do is light has momentum, so you're giving this thing a kick. So that's the first clue, by the way. You're going to interrogate something, you're going to change it. Okay, let's see here. Okay, so you know that if light's going to interact with this atom, even an atom, it's going to push it. Okay, how much? Okay, so it's going to push it. Okay, so remember that light's coming, atoms are coming out, and then we'll have the photon come up from below. Just kind of makes sense. And you'll see it either scatter off the bottom slit or top slit, right? That's the idea. Okay, but light has momentum, so it's gonna change its trajectory. Okay, how much? So delta x, the length of the push, and so it's going to push it in the x direction. And again, x is actually up and down. Now, the way to think about this is that it's going to change the velocity, and of course, it takes a finite amount of time for the thing to travel through this little weird detector. And now, because I'm talking about light, I know what the momentum of light is, so I'm going to be way better off changing velocity to momentum because I know the momentum of light. So you can think of this as like delta P is no light, which is no momentum, versus scattering off light, and then that is h over lambda. Anyway, step by step. Okay, now remember the time it takes? The time it takes is technically 1 over, velocity over length is time, right? Remember velocity is meters per second, so length over velocity ends up having units of seconds, so that's the time. Now what I can do is I see the momentum, that's the momentum of the particle, by the way, and I know that the momentum of light is h over lambda, and what you're left with is L over momentum, momentum of the particle. So that's the particle, our silver atoms, and this is light. This would be the maximum momentum push you could possibly get, the full momentum of light itself. Okay, now, so this is the push. Now let's look at the oscillation. The oscillation is H over P L over A. Did I delete that? Anyway. So that's the oscillation that's the cosine, right? And now here's the push. Okay, the push, you know what, I'm gonna write this in reverse, so here's L over P and H over lambda. I just wrote them, I just switched this. The reason is that what I want to do, oh, wait a minute, did I, no, sorry. Stupid. Sorry. What I want you to do is look at this. Okay. Now, it turns out that you want this to be small. Small compared to the oscillation. If you push the thing more than it oscillates, how can you see the oscillations? Right? In fact, that seems to be probably what's happening. Okay. If this is going to be smaller than this, the only thing that's different is lambda and A. So that means lambda has to be bigger, smaller than the distance between the two slits. Which one? Come on, it's middle school. If this is going to be small, that has to be big, right? Bigger than A. Lambda has to be way bigger than A. Now tell me, how do you distinguish between the two slits if the wavelength of light is bigger than the slits to begin with? Yeah? Okay, what the answer is, U, and the next word begins with a D and rhymes with "ont." It's you don't. If the you cannot observe something smaller than the wavelength of light. Sometimes you can kind of play games with that. I'll gain whose work, but if the wavelength of light is bigger than the slits, you can't tell which slit it comes out of. And if the wavelength of light, if it's bigger, it won't push it around so much, but you don't know which way it came out of. And then vice versa, if the wavelength of light is small enough, it pushes the atoms too hard, and then they won't form that oscillation anymore, which is exactly what that's for real. That's what you get. So anyway, that is an attempt to beat quantum mechanics, and it just completely fails. So I just wanted to show you that. There's a huge history of people, including Einstein, trying to do this, and it never works. Okay, real quick, I just want to go over, I got 2 minutes. Let me just start on a reminder. I know that this is like kind of a little silly and childish, but it's the start of the semester, so I don't want to blow your head off. I do want to remind you of a couple things, and I'm going to just start here next time because I promised I'll be on time. If you don't quite recall this, I just would like you to get up to speed as much as possible. So as I remind you today, that a wave function squared is a probability distribution. And a probability distribution means that the integral of a probability distribution is equal to probability. So that's why, sometimes they're called probability densities. Probability distributions and probabilities, they really have a lot in common. You can really think of them the same way. It's just that by itself, it's just like a function. And if it's integrated, you'll get the number 1.0, which means that if you consider all possible, to turn the math to English, if you consider all possibilities, then you're going to get something. So when you integrate a probability distribution, you get 1.0. Let's see, the second thing is the way you deal with wave functions, and I'll stop here. Just want to remind you, and again, read that half-assed silly book I have, that quantum mechanics is all about eigenvalue equations. When we have operators like the Hamiltonian or momentum times a wave function, you get a number times the wave function. If that fails, then you have yourself a bit of a problem. I don't want to say that you've done something wrong. Let's assume that you always mathematically do things right. If you do not see this behavior in quantum land, it's assuming that you haven't just screwed up, the derivative of cosine is cosine. No. Assuming you haven't done anything wrong, what you've got yourself is you don't understand your system as well as you should. Typically, this means you've got an uncertainty principle coming around, which is what we're going to spend a tremendous amount of time on, uncertainty principles. Okay, the next bits we'll start next time is that the Schrdinger equation is linear, and that means that that you can do things like work with two operators, let's say, I don't know, Hamiltonian plus some other operator, and I'll cover these more. Separability. Okay, so what that means is that we almost always have separable operators, and what that means is that when this matters when you're doing multi-dimensional quantum mechanics, when we're doing X, Y, and Z. What this means is that when we're working with X, Y, and Z, I'm gonna push us to doing multi-dimensional kind of quick. It means that you've got one Schrdinger equation for X, one for Y, and one for Z, and you just multiply the results. And you should have seen that when you were doing undergrad. If you did a little hydrogen atom, you would have seen there was a R theta phi, and we're going to cover some of that. I'll actually restate this because again, I'm already gone over 1 minute. I'll restate this next time. That will be our beginning point, and then at some point, then we're going to start doing flat potentials and barriers and all that stuff. Well, and actually, next time I'll